to live, given the rise of the Chinese middle class. Alright, I won't go into that. Okay, so now the other important result, using reduction. So if you have your two problems A and B, and you reduce problem A to problem B, and you know that problem A is undecidable, therefore problem B is undecidable, well, the language, corresponding language. Language B is undecidable. Alright? Now you can use that idea, that result, which Sipser didn't prove, which I felt a bit odd, because he's using it consistently. You think a really important stepping stone like that would be proved, but no. There are gaps in his story. Anyway, so say now you have some problem B, equivalent, it's language, so it's a language B, and you want to prove that that language is undecidable. In other words, the corresponding problem has no solution, can't be solved using an algorithm, using a Turing machine. So how do you do that? Well, you take some problem, or language, corresponding language, A, and you reduce that language A to the language B that you're talking about, that you're trying to show is undecidable. Okay? Now if you can reduce that way from language A to language B, and you know language A is undecidable, therefore you have proven that language B is undecidable. And that's what we've been doing several times already, and we'll continue to do for a while. Now, so far we've been using, as language A, that we use to prove that language B is undecidable, so far that language A has been ATM. But a bit later into the board, future session, we will use a different language that is undecidable. Well, I can tell you now, I might as well tell you, it's ETM. Alright? Yeah, well, it's the one we're working on right now. Yeah. It's the one we're in the middle of proving just that ETM is undecidable. And then you will use that as language A in proving some other language B is undecidable. So you can see after a while, we start with just one undecidable language, and that's ATM. And then we'll prove a whole bunch of other languages undecidable, and then we can start using those other undecidable languages to prove further languages are undecidable, or equivalently problems are not solvable. So it sort of snowballs, that kind of exponential growth in unprovable problems, unprovable language. And like I say, there's a whole industry. There's a whole lot of researchers working on this. So I can imagine they're probably under the impression of how impotent computers are, if that's all you do all day as specialists. Alright. Okay, so that's a bit of revision on reducibility and how you, the general strategy on how to prove a particular language is undecidable, or correspondingly the corresponding problem is unsolvable. Okay, so we're now getting into the proof of that ETM is undecidable. Now we've done the proof idea, now here's the actual proof. Now you probably remember from the proof idea, we're talking about a modified machine. So we're trying to again, okay, I need a bit of revision, also refresh my own memory on this this problem. So we're trying to show ETM is undecidable. How to do that? Well, but by the way, a more general comment. These proofs, as far as I know, virtually always use proof by contradiction. Right? So that's a commonly used proof technique in this context. I've yet to come across a proof that does not use proof by contradiction. So in this case we do. So we're trying to show that ETM, which is this again, remember? If you want to translate, translate that language into problem, computational problem terms, is you're given, is there a Turing machine, in other words, is there an algorithm that can say whether a random Turing machine accepts no strings? In other words, it's language L of M, L of M is the empty set. That question is not solvable. Right? That's what we're trying to prove. Okay. So, proof by contradiction. So, prove the opposite. Assume the opposite of what we're trying to prove, and what we're trying to prove is that ETM is undecidable. So the opposite of that is that it is decidable. So if it's decidable, that means there's some Turing machine that decides it. So call it R, big R. And then we'll construct another Turing machine, bigger, call it S. And it will use R as a part, as a component. And the task of R is, we know that, it's the decider of this language. Right? And S, what will its task be? Its task will be to recognize the strings in the language ATM. Okay, so S's, the bigger Turing machine, S, its task will be to recognize the language ATM. Alright? Okay, now we're going to talk about reduction. Because Sipser, he doesn't spell that out, so I thought it would be useful to do that. So in this case, how we're reducing what to what? So we're using R to solve S. Okay, we're constructing S using R as a part. So which way are we going? See, so the general strategy, so I'll think in those terms. The general strategy is, if you can reduce a problem A to a problem B, and you know that problem A, or the corresponding language of A, is undecidable, therefore you can conclude that the problem B, or the language B, that you reduce to is also undecidable. Okay, so that's where we want to go. Now we know that ATM is undecidable, so we want to we want to have a reduction from ATM to what? To ETM, I guess. So our problem A is ATM. How to construct a Turing machine